So in this video we're going to continue looking at stationary points, but this time we're going to look at types of stationary points. So we know stationary points occur when the derivative is equal to 0 or we have a horizontal tangent. So here is a stationary point, horizontal tangent, and this shape we call a maximum value, and we call this a turning point because a function stops going up and starts to come down. So it reaches a maximum value for f of x in that particular area. So if I drew the graph and this was f of x, as the x value changes, you can see that the y value is getting larger and larger and larger, and at this point that is the maximum value that we have for y. So this is why we call it a maximum as a turning point. This next one we call a minimum, horizontal tangent, and these two here with horizontal tangents where it's increasing and then it kind of slows and then it increases again. These are what we call stationary points of inflection, and it's really important to use the word stationary to describe these ones where the derivative is equal to 0. Because not all stationary points have a derivative equal to 0, and we'll get to that more in a minute. So the other thing we can talk about, rather than the size of f of x near a turning point, is we can talk about what the gradient of the function is doing. So what kind of slope does this graph have right on either side of these turning points? So our gradient we can think of as a slope. So at our maximum value here, to the left of our maximum, we have a line that's sloping up, so the slope will be positive, and so the gradient is positive. On the other side of the turning point, we've got the line sloping down, and so the gradient will be negative. And so if, as we increase our x value, so our x value is getting bigger as we go across this way, if we stick on the curve, this side, the derivative will give us a positive value when we substitute in x values, and this side, the derivative will give us negative values when we substitute in x values. When we have that situation, we have a maximum turning point. I've color-coded the minimum and the stationary points of inflection the same way. So for the minimum, we have, as we come in from the left, we have a negative gradient, and then as we continue on past the right, we have a positive gradient. For the stationary point of inflection to the left of the turning point, we have a positive value, and even still to the right of the turning point, we'll have a positive value. And in the other stationary point, we've got a stationary point of inflection, we've got negative and negative. So to determine the type of stationary point, there's three different things that you generally use. You can use your knowledge of the graphs of functions if the equation is really simple. So if the equation is in the form of something like a cubic equation, so you've got it in cubic form, and you can see that it's a positive cubic, and then you're going to know that if it's a positive cubic, it's going to come up this first value, whatever that x value will be a maximum, and this second one will be a minimum. The other thing that you can use is that you can use the value of the actual function itself to the left-hand side and the right-hand side of the turning point. So if your turning point is at 2, you could substitute in 1.5 or 1. So on this side to see what the y value is, and you could substitute in maybe 3 on the other side to see whether the graph itself is getting larger or smaller. So if you have a series of x values that you have turning points for, so say for example you know that there's a turning point at x is equal to 1, x is equal to 3, and x is equal to 5 is where you've got your turning points. Then all you need to do is to select an x value to the left of 1, substitute in 0, so find f of 0, find f of 1, find something in between 1 and 3, so find f of 2, and then compare the heights of those particular values. And it'll tell you whether it's a maximum or a minimum. The other thing that you can use is use the sign of the derivative. So to the left-hand side, if it's a positive derivative or a negative derivative, same idea. But you'll be using this idea here where you're looking at a set of x values and picking an x value in between. Specialist maths students, you're allowed to use any specialist maths techniques in methods, so go right ahead and use the second derivative test. And if you're interested in what the second derivative test is, it's basically if you find the second derivative, if it's negative, it means that you have a maximum. If it's positive, it means that you've had a minimum. And if it gives you 0, then it doesn't tell you anything about the point. That does not mean it's a stationary point in inflection. So you're probably best to use one of these two. This is an example of a question where they give you actually a graph of a derivative function and then ask you to identify the values of x for which the original function will have a stationary point. So we know stationary points occur where the derivative is equal to 0. So we want this function equal to 0, which means we're looking at our x-intercepts here. And not only do they want us to find the x values for the stationary point, they want us to tell you the type of stationary point that it is. And so we're going to need to use the information about whether the function, the derivative function, is positive or negative. So we know that the derivative is equal to 0 at x is equal to 1, 3, and 4. And so what we need to do to determine the type of stationary point is look at where the derivative function is a positive value and where it is a negative value. So the actual function itself, we've got y is equal to the derivative function. So on this y-axis, we could actually have f dash x written here, which would mean any y values that were on this part of the axis would be positive. And so you can see that all of these points on the curve here, where I've coloured it in blue, they all have a positive y value, as does this section over here. So these, between -1 and 3, there's a positive derivative. And a positive derivative means that it's sloping up. And so let's have a look at the little table that I've got here. So this little table here has that at -1, x equals -1, x equals 3, and x is equal to 4. I know I have stationary points. And so to the left-hand side of this, I have negative gradient. And a negative gradient means that the line slopes down. So this is, here, the shape of the line. This is the shape of the function. So to the left of -1, the function has a negative gradient, so it's sloping down. Between -1 and 3, the function has a positive gradient, so it should be sloping up. Between 3 and -4, the gradient is negative, so it will be sloping down. And then from 4 onwards, it's positive values, so the line will be sloping up. And so all that's left for me to do is to say, well, if the function comes down and then goes up, it must change here at -1 at a low point here, which makes x equals -1 a minimum. and then between -1 and 3 it slopes up, and then after 3 it slopes down, which means that the function must turn up there, which means that x is equal to 3 is a maximum. And using the same idea, the line slopes down as we come to x is equal to 4. After x is equal to 4, it's sloping up again, which means at this point here, we must have a minimum. Now, I don't know where those maximums and minimums are relative to each other in terms of height. So it might look like this, or it might look like this. I don't know. All I know is that there is a minimum at -1, that's x is -1, that's x is 3, and that's x is 4. That's all I know. And finally, I've included this question from the 2011 Exam 2 paper because if you have a look down here, we're asked about stationary points for this question. It says how many stationary points, and only 9% of students got any marks for this question. And I want to explore why. So this image here is the graph of the function. So it's Exam 2, so you could have drawn this thing on your calculator. But let's start at the start. So consider the function here, find f dash of x. So that's our derivative function there. Explain why f dash of x is greater than 5 for all of x. So this is our formula that we just wrote, and this is the formula for parabola. And it's a parabola, an upright parabola, that's shifted up 5. So if we write something like that, that's why all of the values are greater than 5. And you can see that here in my little graph. Okay, part B. The cubic function p is defined by this particular formula here. So it's a cubic where a, b, c, and k are real numbers. If p has m stationary points, what possible values can m have? So if p has got so many stationary points, what are the possible values for that stationary point? So they want to know how many stationary points. So we know that p is a cubic equation, and so we've got some different shapes for a cubic equation. We've got our cubic equation that looks like this, and we've got our cubic equation that looks like this. And so stationary points we've got here, 2 for that, and 1 for that. Seems too simple. Why did only 9% of kids get this correct? And the reason is that we have just drawn. Have a look at this graph. That's a cubic equation. And how many stationary points does this thing have? The derivative is greater than 5. The derivative is never equal to 0 for this thing. And that is what 9% of the kids missed. They missed that you can have one where m is equal to 0. So our possible values for m are 2, 1, and 0. And then finally, for p, if p has an inverse, what possible values can m have? So for p to have an inverse, it's got to pass the horizontal line test. And so for each one of these options, when m is equal to 2, it doesn't pass the horizontal line test, but for these two, it does. And so the answer, m is equal to 1, m is equal to 0. So, my exam hint at the bottom. Not all cubics have a stationary point of inflection. They will definitely have up here, we've got a point of inflection. We definitely have a point of inflection because it stops curving up. point of inflection. So it stops curving one way and starts curving the other, which is the definition of a point of inflection. But the derivative does not go to zero, and so it's not a stationary point of inflection.